Have you ever looked up at the night sky and wondered, what is pushing our universe apart? Not pulling things together, not keeping them in balance, but actually pushing them apart faster and faster like an invisible hand stretching the fabric of space. It's not gravity, it's not stars, it's not even black holes. It's something we can't see, don't fully understand, and yet it makes up most of our universe. This mysterious force is called dark energy, and it's one of the biggest puzzles in all of physics. But what is it really? How do we even know it's there, and what does it mean for the future of everything, including us? Let's explore the mystery of dark energy and how it's reshaping our understanding of the cosmos. To understand dark energy, we have to go back about 100 years. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He noticed that distant galaxies weren't just drifting around in space, they were moving away from us. And not just a few galaxies, all galaxies. The farther away they were, the faster they were receding. This led to a stunning realization. The universe itself is expanding. Imagine blowing up a balloon with tiny dots on its surface. As the balloon grows, the dots move away from each other. The surface of the balloon is like our universe. Every galaxy is moving away, not because they're traveling through space, but because space itself is expanding. At first, scientists thought this expansion might eventually slow down. After all, gravity pulls things together, right? So over time, maybe gravity would halt the expansion, maybe even reverse it. But then something completely unexpected happened. In 1998, two independent teams of scientists studying distant supernovae, those powerful explosions at the end of a star's life, found that the universe wasn't just expanding, it was expanding faster over time. The universe was accelerating. Think about that. Gravity should be slowing things down, not speeding them up. So something else had to be acting, something with a kind of anti-gravity effect. This was the birth of the idea of dark energy. So what is dark energy? Honestly, we don't really know. But we do know this. Whatever it is, it seems to make up about 70% of the entire universe. To break it down, normal matter, everything we can see, touch, and measure makes up just about 5%. Dark matter, a mysterious, invisible type of matter, makes up around 25%. And the remaining 70%, that's dark energy. It's like we're living in a house where only one room is lit. We're guessing what the rest looks like by the creaks in the floor and the movement of air. So how do scientists even detect dark energy if they can't see it? The key lies in how the universe expands over time. By observing supernovae, the cosmic microwave background, and how galaxies are distributed on large scales, scientists have noticed that something is driving the expansion, not just maintaining it, but accelerating it. Think of it like this. You throw a ball into the air. Gravity slows it down until it stops and falls back. That's what we expected from the universe, that gravity would gradually slow the expansion. But instead, it's as if the ball suddenly speeds up on its way up, as if an invisible engine kicked in, pushing it harder. That engine is what we call dark energy. But if we don't know what it is, are there at least any ideas? Yes, several. Here are the main ones. 31. Einstein's cosmological constant. Einstein once added a term to his equations of general relativity called the cosmological constant. He thought the universe was static, neither expanding nor contracting. So he added this constant as a kind of repulsive force to balance gravity. When Hubble later discovered the universe was expanding, Einstein called it his biggest blunder. But here's the twist. Maybe it wasn't a blunder at all. The cosmological constant might actually be real, representing the energy of empty space itself. As space expands, it creates more space, and that new space comes with its own energy, which pushes things even more. Theory 2, quantum vacuum energy. According to quantum physics, even empty space is never truly empty. Tiny particles and their antimatter twins pop in and out of existence all the time. These fluctuations could generate a small but constant pressure that, over cosmic distances, adds up to a powerful force. The problem? The math doesn't quite work yet. The theoretical prediction of this vacuum energy is much, much larger than what we observe. That means we're either missing something or we're not looking at the full picture. Theory 3, a new kind of energy field. Some physicists propose that dark energy isn't constant, but comes from a dynamic field that changes over time. They've even given it a name, quintessence. This would mean dark energy might grow stronger, weaker, or behave in strange ways as the universe evolves. Theory 4, we don't understand gravity at large scales. Another possibility is that we simply don't understand gravity well enough. Einstein's equations have passed every test within our solar system, but what if, over billions of light years, gravity behaves differently? Maybe it weakens in ways we haven't noticed yet, or new forces appear. This would mean rewriting some of our most trusted scientific laws. So if we can't see dark energy and we're not exactly sure what it is, what proof do we really have? Let's go through the evidence. 1. Supernova observations. These exploding stars serve as standard candles. Their brightness tells us how far away they are. When we compare their distance to how fast they're moving away, we can trace the universe's expansion history. And they clearly show the expansion is speeding up. 2. Cosmic microwave background, CMB. This faint afterglow of the Big Bang holds a wealth of information. By studying the tiny temperature fluctuations in the CMB, scientists can determine how the universe evolved, and it all points to dark energy being present. 3. Large-scale structure of the universe. Galaxies are not randomly scattered. They form web-like patterns shaped by gravity and the expanding universe. The way these structures grow and stretch fits best with a universe being pushed apart by dark energy. Now the big question, what does dark energy mean for the future of the universe? If dark energy remains constant, the universe will continue expanding forever. Galaxies will drift so far apart that their light won't reach us anymore. Over time, stars will burn out and the universe will grow dark, cold, and quiet. This is sometimes called the Big Freeze. But if dark energy grows stronger over time, if it increases in intensity, we could face a dramatic ending, the Big Rip. In this scenario, dark energy becomes so powerful that it overcomes all other forces, not just pushing galaxies apart, but tearing stars, planets, even atoms to shreds. Space itself would be ripped apart. It sounds like science fiction, but the math says it's a possibility. Of course, all of this is based on our current understanding, which is still evolving. And maybe, just maybe, we'll discover something entirely unexpected. Here's what makes dark energy so fascinating. It's a reminder that we're still at the beginning of understanding our universe. In a way, it's humbling. We humans, sitting on a tiny rock, orbiting an average star, trying to make sense of something that spans billions of light years. But it's also exciting, because every new discovery opens the door to more questions, more exploration, more wonder. So the next time you look up at the night sky, remember, we don't have all the answers, but we're asking the right question. And in the vast silence of space, those questions might just lead us to the greatest discoveries of all.